Have you ever really, truly thought about what's going on inside your laptop when you pick it up? I mean, it hums, it gets warm, it connects you to pretty much everything. We tend to think of it as, a solid box full of parts. But today, we're going to look at it in a totally new way, a perspective that honestly changes everything. Right there. That one idea is the key. Forget about static components for a minute. I want you to start thinking of a computer as a symphony of controlled movement. We're talking about electrons zipping back and forth, invisible fields flexing and relaxing, and these tiny little crystals just ticking away in perfect time. So this is the lens we're going to be looking through today. It's called motion theory. And what it does is reframe the entire machine not as a thing, but as a dynamic system. And when you see it this way, you realize that everything a computer does, from the moment it boots up to loading your favorite website, is really just a form of structured, organized motion. To really get this, we're going to go on a journey. We're going to follow the path of that motion, starting from the instant you plug your computer into the wall, and we'll follow it all the way to the light that's literally hitting your eyes from the screen. Our journey starts with something big. It starts with taming the raw, kind of chaotic energy that powers our whole world. This very first step is all about taking something massive and wild and shrinking it down, making it stable enough for the super delicate electronics inside the machine. See, the electricity coming out of your wall socket isn't some nice, gentle stream. A much better way to picture it is as a city-scale oscillator. Just imagine this huge invisible pendulum swinging back and forth 60 times every single second. That's the raw power we're starting with. So, how in the world do you tame something like that? Well, that's the job of the power supply. It's basically a motion taming machine. First, it rectifies the flow, which means it forces that wild swinging motion to go in only one direction. It's still pulsing, but it's a start. Then, it chops that flow into millions of tiny little pieces every second. And finally, it smooths it all out, creating the nice, steady, calm direct current that the computer actually needs to survive. Okay, so where does all that smooth, calm power go? It flows right onto the motherboard, which you can think of as this vast, intricate river delta. The big copper layers, those are like seas of charge. And all those tiny little lines you see, the traces, those are the canals, precisely guiding this electrical motion to every single component that needs a drink. All right, so we have a steady, guided flow of energy. That's great, but that's just power. How does a simple current start to, think? How does mere motion become actual information? Well, the answer lies in giving all of that motion a rhythm, a heartbeat. And that brings us to what you could call the clockwork core of the whole operation. Buried deep inside every computer is this tiny, tiny sliver of quartz crystal. And what's amazing is that when you pass electricity through it, it physically vibrates. It sings at an incredibly stable and predictable frequency. This creates a perfect, unwavering rhythm, a standing wave, that acts as the master metronome for the entire synchronized dance happening inside the computer. So we've got a heartbeat. Now we need a way to actually control the flow. And that, my friends, is the job of the transistor. Billions of them. The best way to think of each one is as a microscopic valve for electron motion. A tiny little electric field can either open that valve or close it, either inviting the current to flow through or blocking it completely. And that right there, that is how we sculpt mere flow into what you could call decision-grade motion, a 1 or a 0. Now, here's the thing. Every single time one of those billions of valves opens or closes, it has a real physical cost. It takes a tiny bit of energy to make that switch happen, and that energy has to go somewhere. So the heat that you feel coming off your laptop? In this view, that heat is just spent coherence. It's the disorganized, leftover energy from billions upon billions of precise decisions being made every single second. Now, let's zoom in on the CPU. It's not just random chaos in there, it's a masterpiece of traffic engineering. Instructions flow through this beautiful 4-stage pipeline, almost like an assembly line. An instruction gets fetched, then it's decoded, then it's executed, and finally the result is written back. It's this continuous, perfectly timed flow of operations. So the system is incredible at processing information at lightning speed. But processing is temporary, right? If the motion stops, the information just vanishes. So how does a system that is built on constant motion remember anything at all? The act of remembering, when you think about it through this lens, is really just about finding a way to pause the rhythm. It's about creating these little pockets of temporary peace where a pattern of motion can be held still, just for a moment. And it turns out there are a few different ways the computer does this. Your main system memory, the DRAM, that's like parked electron motion in these tiny little buckets that are constantly leaking. The superfast cache right on your CPU, the SRAM, that's more like a self-sustaining standing digital wave that holds its own shape. And then you have your SSD, which uses flash memory to literally trap charges in tiny gates for years. What this means is that memory isn't some abstract concept, it's deeply physical. To remember a single bit in DRAM, the computer has to constantly fight against entropy. It has to keep pumping that motion back up before it just fades away. Forgetting isn't just a metaphor. Forgetting is a real physical process. Forgetting is a leak. All right, we have come so far. We've tamed the wild motion from the wall, we've given it a heartbeat, we've sculpted it into logic, and we've even learned how to make it pause and remember. Now it's time for the final act, making all of this invisible internal motion visible to us. This is the job of the graphics processing unit, the GPU, and it is an absolute engine of parallelism. It has thousands of tiny processing cores, these parallel loops, all working together at the same time to calculate the color and the brightness of every single pixel on your screen, over and over, dozens of times a second. So how does all that math become an image? Well, it starts with a backlight, and that's really just a constant, steady flow of white light. Think of it as a photon flow. Okay, so in front of that steady flow of light is a grid of millions of tiny liquid crystal cells. And based on what the GPU calculated, these cells physically twist and untwist, using tiny electric fields to filter and retune the polarization of the light that's passing right through them. And this is the final amazing transformation. The image you see on your screen isn't a static picture. It's a performance. It's millions of light rhythms being summoned in real time by incredibly precise electric fields, all of which started as that chaotic flow of electrons from the wall. So when you step back, when you look at the whole system from the wall socket all the way to the screen, you finally see it for what it truly is. It's not a dead box of silicon and plastic. It's a cathedral of synchronized motion. A place where countless layers of loops are holding, transforming, and routing motion with just breathtaking precision. And that really leaves us with this final, powerful thought. The real magic isn't that a lump of metal and sand can somehow think. The miracle is that we've figured out how to organize motion so perfectly that it can hold on to a memory of yesterday, and then use that memory to draw a picture of tomorrow on a simple sheet of light.